5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Your job title is the TOI embedding lead for TESS, the Transiting Exoplanet Survey Satellite. Can you describe your average day when it comes to selecting objects for TESS?
All right. So my average day typically entails, first of all, this is a tricky question because there's so much little parts to my job, but really the main part is the vetting process, which is where we review all of the reports that come out of TESS. So TESS will trigger on any dimming in brightness for the host star and flag those as transits. But we need independent vetters to go through and look at all of those signals and determine if they look like planets or not, because there are other astrophysical and other objects that can cause those same effects. So it could be false positives like eclipsing binaries or stellar variability or something causing those dips in brightness instead of planets. So what we need to do is go through and have our expert vetters kind of determine if these signals seem like they're coming from a planet or if they're coming from something non-planetary. So how that works is once the reports are generated, I upload those onto our vetting site. Then the vetters will look at them individually and see if they look like a planet or not. Once each target has been vetted 3 times, if someone thinks it could be a planet, we look at it in what we call group vetting, where 3 vetters that are expert vetters will go through all of the potential planets and decide which ones look good enough to make TOIs, which are the TESS objects of interest. And those are the candidates that we really think might be planets.
I'll backtrack a little bit. Can you describe the TESS and its mission goals?
Sure. So TESS is the Transiting Exoplanet Survey Satellite, and it's looking for planets smaller than the size of Neptune around bright stars that are good for follow-up further research with new telescopes like James Webb. So particularly, we're looking for a lot of planet candidates that we can find out information about the atmospheres. So new telescopes like James Webb have the capability to tell us more about the atmosphere of these planets. And once we have selected these targets with TESS that are kind of ideal candidates, we can go back to those with James Webb and find out more information.
The human eye, the human eye can see up to a magnitude of around 6. The planet Neptune's at 7.8, so we can't see it without a telescope. Can you give us an idea of the faintest star TESS can see?
Sure. So the faintest star that TESS can see is probably about 10,000 times dimmer than what we can see with the human eye. So just as a comparison, that would be like if the dimmest star that we can see with our eye was as bright as the moon. The dimmest star that TESS would be able to see is the brightest star in the sky, Sirius. So it's about a 10 magnitude difference, I think, but really big difference. So the difference in brightness between the full moon and the brightest star in the sky.
There are other ways to detect extrasolar planets. What makes discovery by transit the most efficient way?
Transit discovery is the most efficient because we can look at a large number of stars at once. So we can look at thousands of stars at once and observe those simultaneously. Whereas with other methods, we need to specifically focus on one target at a time.
If we glance at a clock quickly, we never notice the hour hand move. How long does TESS need to look at a star for a transit? Because it's not possible to look at a star for months on end, right?
Basically, to observe the transit, what's really tricky about this is the actual transits themselves aren't too long. They're only about between a few hours, or I think the longest one that they've found so far with TESS is about a day. So the transits themselves don't actually take a long period of time, but for detecting planets, we want to find multiple transits, and that's where it gets tricky because the longer period or the longer it takes those planets to move around their suns, the longer it'll take for us to observe more than one transit. So what TESS does is it views the sky in sort of broken up sectors. So first it looks at the northern hemisphere, then it looks at the southern hemisphere, and it breaks those up into sectors, which are kind of just strips from the pole to the ecliptic. And since we can revisit those sectors, TESS just kind of rotates throughout the sky and tries to look at the whole sky. And even though we don't have continuous observations for all these planets, we can get enough data as TESS continues that we can hopefully find more than one transit and detect planets on these stars.
Planet hunting is relatively new, and it wasn't until 2002 that a planet was discovered by the transit method, which TESS utilizes. Being a new field of astronomy, are there new things being learned that also help studies beyond exoplanets?
So I guess other than exoplanets, the main things that TESS is really used for is learning about planets in our own solar system. So it's helping with the search for planet 9, which is this potential 9th planet in our solar system. And then other than that, it's also starting to be used for more research towards the galactic side of astronomy. So looking for supernovas and transients and other far out objects like that.
The Kepler telescope was also tasked with finding Earth-sized planets orbiting other stars. What was the greatest contribution that the Kepler Space Telescope made to enhance the TESS mission?
So really the biggest contribution from Kepler is that Kepler really just showed us the variety of planets that exist. So before Kepler, we really were expecting a lot of the exoplanet systems to model our own solar system. So kind of have a similar setup where we have the interior planets, exterior planets. But Kepler found a lot of other types of planets with different densities around different types of stars. There were planets around binaries and stuff like that. So Kepler has really opened our minds a bit, I guess, to all the different types of exoplanets that are out there. And going off of TESS, we've been able to just kind of continue looking for those planets that might not be like those in our solar system. Like Kepler found a lot of super Earths, which we don't even have in our solar system. And those are planets bigger than the Earth, but smaller than the giants. So there's a lot out there that's different than what we might expect.
Dr. Stephen Hawley, an astronaut and friend of the Cosmosphere, submitted a question that's about super Earths. He says he's asking, from the Kepler mission, we learned several surprising things. We discovered hot Jupiters and super Earths. We also found that planets around red dwarfs were far more common than we expected. Of course, Kepler provided our first detailed look at the transiting exoplanets. However, are there similar surprises that TESS has produced?
All right, so TESS has really found some, I guess, new varieties of planets that Kepler didn't find too many of. So TESS has found some hot Neptunes, which are pretty rare to find. They're still pretty rare in TESS, but what these are we found a lot of hot Jupiters with Kepler, which are Jupiter-sized planets close into their stars, but there was a surprising lack of Neptune-sized giant planets close to their stars, which TESS has found a few examples of, but still has that gap. So TESS is telling us a bit more about that. And then really the other part that TESS has built out is finding a lot of gas giants around smaller hosts like white dwarfs and M dwarfs, which is a new development from Kepler. For example, TOI 530b is a gas giant that's a bit smaller than Jupiter, and it orbits a M dwarf, which is pretty rare. So we haven't really seen too many of those before. I think that's only the 6th example that we found.
M-type dwarfs make up a majority of our stars in our Milky Way galaxy, so mathematically will produce the best chance at producing exoplanets. Are these type stars the best at creating optimal habitable zones, or are other type stars better?
Yeah, so M dwarfs are better in a way because they have a longer lifetime than our star does. Our star is a sorry, my cat just walked into the door. But our star is a G dwarf, so these M dwarfs live longer than our star would. So they have a longer time for life to develop, potentially. But the downside of M dwarfs is that a lot of times they are variable stars. So they'll have a lot of flares, which could make basically what you want for life is to have kind of a nice and consistent environment around the stars. You don't want to be too close, you don't want to be too far, but you also don't want to have too much variation in the star that could affect life on the planet. So M dwarfs are good in a way because they have a longer lifetime and planets can be closer in, which would be easier to detect since the stars are less hot. But there might be those flares that you want to watch out for.
You don't want to get your planet shot by a flare.
No.
All right, what happens next when TESS finds a star that has a transit event? How common are false positives?
So false positives are relatively common. I would say that maybe about 20% or so of the TOS released so far have been false positives. But when we find a star that we think is a planet, pretty much what we do is we try to alert conservatively. So if we think there's a chance it could be a planet at all, we alert it as a potential planet, as a TOI. And for that reason, a lot of them do end up being false positives. But we want to make sure that we're not missing any potential planets. So we err on the side of conservation with that.
What causes these false positives? What's the most common reason?
The most common false positive is eclipsing binaries. So that can happen where there's actually a star orbiting around the star that we're seeing rather than a planet. And then there are also other cases where we have what we call a nearby eclipsing binary, where there's an eclipsing binary in the background of the image and that bleeds into the signal. So we think it looks like a planet since it gets a little bit diluted with the target star, but actually it's just a eclipsing binary in the background.
Dr. Hawley has another question for you. In the past, the Spitzer infrared telescope teamed up with Kepler and TESS to confirm candidates, but Spitzer recently retired. Another infrared telescope is just launched, the James Webb Space Telescope, which everyone has been anxiously awaiting for it to take its first flight. Are there some good candidates identified for follow-up with the James Webb Space Telescope?
Yeah, definitely. I don't have an exact number on the amount of candidates, but that's been a really big portion of TESS's goals to find these good candidates for follow-up. A few that come to mind is one of them in particular is a hot Neptune, which are those kind of rare Neptune-sized planets that are close to their stars. But an example that TESS has found is LTT 9779b, or TOI 193. And that's a confirmed planet by TESS. That's a hot Neptune, and it's supposed to be pretty amenable to atmospheric follow-up. So we want to learn more about the atmospheres of these hot Neptunes specifically, because they kind of fall in this region where we don't really know too much about these planets, and we want to know why there are so few of them.
When you have confirmation that you have found a planet and it resides in the habitable zone, what are some things that could render it uninhabitable?
Yeah, so some things that could make the planet uninhabitable are one big factor is the atmosphere. So in order to sustain life, we have to have some sort of atmosphere that can keep the climate on the planet amenable to life. But another factor is whether or not the planet is tidally locked. So what happens with tidal locking, we see this with our moon, is that the object orbiting the, well, with our Earth and the moon, it's the moon orbiting the Earth, but it's tidally locked. So the moon rotates at the same period as it moves around the Earth. So we always see the same side of the moon. But this can also happen with exoplanets, which is bad for life because if they're tidally locked with a star, they're always going to have one half of the planet facing the star and the other half of the planet always facing away. So we get a really big temperature difference where one side is really hot, one side is really cold. So that could definitely be a barrier to life too. But a really big point about habitability is just that we really don't know what to expect. We try to base our estimates off of what life is like in our solar system, but just as planets are different in different solar systems, it's likely that life will be different as well.
Can you tell us about some of your favorite noteworthy discoveries of TESS since it was launched in 2018?
Yeah, so a more recent one is, I think it was the beginning of last year, they found a TOS 674b, which has water vapor in its atmosphere. So that's an exciting one. Other than that, one that comes to mind is TOS 700. So that was actually a multi-planet system where there was a Earth-sized planet in the habitable zone. And it's around a cool M dwarf as well. So going back to those. But that was an exciting example too, because TESS wasn't particularly meant to find these Earth-sized planets. Like Kepler specifically was looking at these dimmer stars, looking for these Earth-sized planets, but TESS is just trying to get a full survey of the sky. So the fact that we were able to find a Earth-sized planet is a good sign for future studies.
To date, how many planets have been candidates? How many planets have been candidates that TESS has discovered, and how many planets have been confirmed?
Sure. Can I actually just add one last statement about that last question?
Yeah.
I don't know if this can be put in later. Just another planet that is a really neat one is GJ 367b. And this one's cool because it's a really small planet. So it's a lot smaller than the Earth. And it's an ultra short period planet too. So it's really close to its star. But that's an example of how TESS can find these really small planets, even smaller than the Earth. So it's a good sign for looking for more Earth-sized planets. But yeah, going back to the other question.
Yeah, how many candidate planets has TESS discovered, and how many have been confirmed?
All right, so there are over 5,000 candidates currently. So TESS has found a lot of candidates. Of those, about 170 have been confirmed so far.
Can you describe some rocky planets discovered in the habitable zone and what makes them good candidates for supporting life?
Sure. So one example is Kepler 186f, which is around M dwarf. It's a particularly quiet M dwarf, so there's not a lot of flares. So that is looking good for life.
In your opinion, what would be considered the greatest triumph of TESS?
So what I think is the greatest triumph of TESS thus far is really just that it's getting such full sky coverage. So previous exoplanet missions like Kepler focused on a specific region in the sky, but TESS is taking these full frame images of the entire sky. So we're finding a lot of new planets and also just getting more variety of planets as well. Since we're not looking in a specific region, we're just trying to find as many planets as we can around bright nearby stars.
I got some teacher-related questions. What is one piece of advice you would give to a first-year physics teacher?
Sure. Really, I liked what you were saying at the beginning of the interview about discovery-based learning. That's really the biggest advice I would give is just if you can ever get students to discover what you're trying to teach and find it themselves through hands-on lessons, that's really the best way to do it. And especially with something like physics, where it's really in the world all around us, it's really important to just look at where we see physics in the world around us and see how objects move and try to figure out whatever we can experimentally.
Is there a specific teacher or mentor that helped you get to where you are now?
Yeah, so I guess the first one that comes to mind, I've had a lot of different teachers that were very good teachers, and I think that's why I got into the teaching field and also just into academia in general. But my cooperating teacher when I was student teaching was very helpful and I think shaped like why I use discovery style investigation so much for teaching. One of the like mentors I've had most recently is actually one of the grad students from the program that I was in at Wesleyan. And he was in the master's program there the year above me, and he was also working on exoplanet research. And he was working at this position right before me as well, and just kind of has always been a good resource to go through for any exoplanet questions. And that's kind of how I decided to go into exoplanets, because originally I was looking at a bunch of different exoplanet fields.